Okay, so today is the last lecture. I'm going to say this is going to be kind of an optional lecture, okay? We're going to cover two constructions of the real line, okay? So on your last homework, you kind of have one construction constructed from certain equivalence classes of Cauchy sequences. We're going to see two more in this lecture. It's not going to be on the final, but I think it's kind of good to know about, okay? And I certainly won't have time to present all the details of it, but I'll be able to tell you at least, the definitions and say a couple of the properties, how you get, enough of the properties of R that you want. Okay, so the first construction is due to Dedekind. So these are called Dedekind cuts. Okay, so let me just, before I start saying what these are, again, remember what we want to do is we want to define a set. We want this set to have certain operations, so ways to combine elements of the set to get new elements of the set. They should satisfy these axioms. And then what we really want then is some ordering. We want completeness, okay, some least upper bound property, and that it turns out that's sufficient to get the real numbers uniquely, okay? So let me give you the idea, okay? So we have kind of the real numbers here, okay? And remember, the problem with using the rational numbers is that there are these holes, all right? We have something like the square root of 2, which is a real number, which is not a rational number, okay? So if we just concentrate on the rational numbers, you get quite a lot of holes because there's missing terms, okay? And what the idea of Dedekind cuts is to think of this hole not really as a hole in the rational numbers, but as defining two subsets of the rational numbers, okay? So there's the set of rational numbers before the hole or less than the hole, and the set of rational numbers above the hole. So before, when we had the square root of 2 was equal to the supremum of the set, x in q, x squared is less than 2. This is a similar idea, but we're going to think of the square root of 2 not as the supremum, but just identify it with these two sets, okay? So that's what the square root of 2 is going to be. It's going to be a subset of the rational numbers. Okay, so let's see the formal definition. Okay, so a Dedekind cut which I'll call S, contained in Q, okay? So the first is that, so it's a subset which satisfies the first, which is first property, is that it's a proper subset, okay? So S is not empty, and S is not equal to Q, okay? The second property is that if a rational number is in S, and there's some, I'm going to call this T, in the rationals with T less than R, then T is in S, okay? So if you're in S, you contain all rational numbers below S, okay? And the last condition is that if R is in S, there exists some rational number with S greater than R and S in S, okay? Okay, so let me give you an idea of how what this looks like, right? What you should think is that it's going to be the same picture essentially as above. Okay, so a Dedekind cut should look something like a ray. Of course, this is only in the rationals. Okay, so somehow I'm drawing here like the rational number line. Okay, so it's a ray pointing to the left. Okay, so it's not all the rationals. If you have any such number, if you ever find a rational in here, you know that it has to contain all the rationals less than it. And finally, you also know that you can find a rational number greater than it, okay? And still in the set. So you should think that what we've done, we now have the idea, or defined, the open ray negative infinity the square root of 2, okay, using only the rationals. But of course, we can do this not just for the square root of 2, but for any real number, okay? Okay, so let me give you some examples of what Dedekind cuts are, what subsets the rationals are Dedekind cuts. Okay, so the first is for any real number, R, the set negative infinity to R intersect Q is a Dedekind cut. Okay, so this is slightly misleading, right? I mean, you can check that, if you know what the real numbers are, they will certainly satisfy the above three properties. But again, remember, we're kind of already, we wanted to find the real numbers using these cuts, okay? But in particular, I could take, for example, negative infinity to 0 or negative infinity to p over q, any rational number, intersect the rationals, and this will be a perfectly good Dedekind cut, okay? So a non-example would be just the closed interval, negative infinity to p over q, for any rational number, okay? So this satisfies 1 and 2, okay, but not 3. Okay, so now let me give you the kind of the definition of R as a set, okay? Well, it's just, R is equal to the collection of cuts, okay? So it's a kind of, once you've defined what a cut is, it's easy at least to define R as a set. Of course, we still haven't defined the operations or the ordering, but this is our starting point, okay? So we think of the rational numbers contained in the real numbers. So now remember, this is now subsets, okay, certain subsets of the rationals. So the way that you identify a rational number with a real number is precisely thinking of the rational number p over q going to the Dedekind cut negative infinity to p over q. Okay, so let's see what addition should be. So now operations. Well, luckily we've kind of seen these operations before when we were working with the real numbers, okay? So for two Dedekind cuts, S and T, we define S plus T to be the set, well, which we did define before, which is just all sums, S plus T, for S and T and T, okay? Now what we have to check, okay, it's not immediately obvious, is that S plus T is a Dedekind cut, okay? So otherwise this wouldn't be a well-defined operation, okay? And maybe I will just leave this for you. Okay, it's pretty simple actually. Now, if I've defined this plus operation, I should of course also, work out what the identity should be. In other words, I want to know what 0 is, okay? So 0 is just going to be the Dedekind cut rational numbers which are less than 0, okay? And you can also check that S plus 0 is equal to S for any Dedekind cut S. So maybe I'll do this one for you just to give you kind of an idea of how these proofs go. Okay. So you want to show that two real numbers, I'll just write this out, want to show two cuts are the same. Okay. So this comes down to showing that two subsets of the rational numbers are the same, which means that you better use double containment. Okay, so let's show that S plus 0 is a subset of S. Okay, so we let S plus A be in S plus 0, okay? So this means, S is in S, and A is less than 0, okay? And what you want to show is that this is a subset of S. So you're adding a negative, you're starting with an element S, and adding a negative number, okay? So in this case, since S minus A is less than S plus A is less than S, we have that S plus A is in S by property 2 of being a cut, okay? So since if S is in S, then you know that any rational number less than S is also an element of S. S plus A has to be in there as well, okay? So you can think of this as, just add take an interval from negative infinity to S and add in the interval negative infinity to 0. It'll be the same interval. Okay, this is just kind of going through that argument. Okay, so essentially how all the proofs go, though, you have to convert everything into working with subsets, because that's how you've defined the real numbers. Okay, so to show this way, S is contained in S plus 0. Well, we let S in S. Okay, now notice that the elements of 0 are all strictly less than 0. Okay, so if I take any element which is, in this set 0, and add it to S, I'll have something strictly less. So that seems like it might be an issue, right? Because you're making everything smaller than the element you're interested in. Okay, but by property 3 of being a cut, okay, there is an S prime in S so that S is less than S prime. Okay? So we're using the fact that we can always find a larger element of the set S. Okay, so if you're a cut, you can always find a rational number that's larger. So then we have S prime is in S, S minus S prime is in 0, and S is equal to S prime plus S minus S prime. Okay? So you find your element S, you find an element that's a little bit bigger, and then you add an element that's slightly negative, which is contained in your 0 subset. Okay? So that's the double containment proof. Okay, so let me actually go to the ordering, because it's easier in this case to define the ordering rather than multiplication. Okay, so the ordering on the set of Dedekind cuts is just proper containment. Okay. So in other words, S is less than T if and only if S is a proper subset of T. All right, and if you think about the idea of two kind of left rays in the rational numbers, this makes perfect sense, right? The ray corresponding to the larger rational number is going to correspond to the larger set. Okay, so it's easy to check that this relation satisfies the relations that you want. Okay, this relation satisfies trichotomy. Okay, so this was S is less than T, S is equal to T, or T, is less than S. You get immediately from the idea of being contained in a subset that if S is less than T and T is less than U, that S is less than U. Okay, so you get transitivity. And also additivity, that if you take S is less than T, then U is plus S is less than U plus T for all U, okay, for all real numbers. This is again just if you have one subset, if S is a subset of T and you add the subset U to both, you'll get another subset. Okay? So from this, we can define the idea of a least upper bound or greatest lower bound, etc. Okay? Okay, so let me just kind of prove one more thing about this set of Dedekind cuts, okay? Which is that, say this is a lemma, R, okay? So by what I mean, the set of Dedekind cuts with the ordering that I've defined so far, okay, so maybe I'll just say this, R with this ordering satisfies the least upper bound property. Okay, so that's a key property for the real, of course, for the real numbers to have. Okay, so what I mean then is that any bounded subset has a least upper bound. Okay, so maybe it's not even obvious what a bounded subset is. So what this means here is that, well, there exists some real number, okay, which I guess I'm calling S, okay. Maybe I'll call this any bounded subset X has a least upper bound. so that x is in X implies X is less than S. Okay? And what this really means is that this is a Dedekind cut, and it's contained in the Dedekind cut S. And this holds true for all elements in X. Okay? So this should give a hint of what the least upper bound is. Okay, so the least upper bound is just the union of the Dedekind cuts. Okay? So you should think, well, if you're going to be an upper bound of this set of subsets, you should contain them all. And then the smallest set that contains all of these Dedekind cuts is just the union of the Dedekind cuts. Okay? So let's prove this. Well, the first thing, of course, that we have to check is that this union, we have to check this union is a Dedekind cut. Okay? So let's just check the properties. All right, so since every x in X is contained in this cut S, so is the union. So therefore, this union is not the whole real numbers. Okay, so is not the whole rational numbers, and is not empty, since the original sets were. Okay, so that's the first condition to check. It's easy to see that if you have S in the rational numbers, and S is less than T for some T in the union of these cuts, union S, then S is also in this union. Okay. And that's just because each of these cuts is a Dedekind cut. So if T is in particular in some element X, and therefore X contains all of the rational numbers below T, so in particular it contains S. Okay. Finally, you just have to check that if S is in this union of rational numbers, the union of these Dedekind cuts, then we have to find some larger rational number, which is also contained in this union. Okay, so if S is in 1, then of course S is in some element X, right, for some X. And therefore, there exists a rational number in X so that S is less than S prime. Okay? And then, of course, S prime is in the union of these Dedekind cuts. Okay? So that's condition 3. Okay? So the union of any number of cuts, as long as it's bounded, as long as it's contained in some larger cut, is going to be a cut itself. It's also an upper bound, right? So it's certainly the union is an upper bound for X, okay? Since, well, the set X is contained in the union of the X's for all X, okay? But on the other hand, if, X is contained in S for all X in S, then the union of these is contained in S, which means that this statement here is precisely the statement of being a least upper bound, okay? If the ordering is depending on being a subset rather than being less than as a real number. Okay, so therefore the union of these is the supremum of X. Okay, so that's essentially all I'll say about Dedekind cuts. Let me just say multiplication is slightly trickier. Of course, this is, it's a big thing that I'm avoiding. The main problem is that the product of two Dedekind cuts is not a Dedekind cut. Okay? So you can just think of, what if I take 0, which I'm thinking of as this ray here, times 0, right? This ray here, then, so I'm taking all the, negative rational numbers times all the negative rational numbers, and this all of a sudden produces for me all the positive rational numbers, okay? So I can't look at something like ST for S and S and T and T, okay? So it turns out the way to do this is to instead just define multiplication on the positive rational numbers, and then you just kind of, say that, the product of two negative rational numbers is the exact same as the product of two positives. So I won't go into all of that, but that's the main obstruction there. Okay, so let me go on to the next part. So this isn't really, I guess I won't call this a construction of the real numbers, but I'll just say the real numbers as decimal expansions. Okay? So this was something that we had kind of seen before when we were doing countability arguments without ever really, justifying why you could think of a real number as a decimal expansion. Okay? So that's what we're going to do. We're not going to really construct them in the same way as we did cuts, just assume that we have the real numbers and show, how to identify them with a set of decimal expansions. Okay? So let's take a real number just between 0 and 1 for simplicity. And S is going to be the digits 0 through 9. All right? And let's just assume that X is not a rational number. All right? So how do you make a decimal expansion for X? All right? So you take 10X. Okay? So this is some number between 0 and 10. Okay? So therefore, there exists, which I'll call A1, in S, which is the largest element less than X. Okay? And you can think, well, if X had some decimal expansion, you're just fine that this is going to be the first digit, right? But this is the way that you construct the first digit. You multiply your thing by 10 and take the digit that is the largest one but smaller than it, okay? So what do we have then? Well, what we know is that 0 is then less than X minus A1 over 10, which is less than a tenth. Okay? So you can see this just by multiplying by 10, right? So just multiply by 10, and I'm using the fact that X is irrational, right? Otherwise, I might have been able, notice that there's never going to be an element in S which is actually equal to X, or equal to 10X, right? Because X is irrational. Okay, so now we do the exact same thing. Okay, so let A2, well, essentially the exact same thing, be the largest element of S, which is less than 100x minus 10 times A1. Okay, so what you should be thinking of is that, well, say 100x is somewhere between 0 and 100. Let's say it's around 54 or something, right? Then your A1 that you would have gotten by multiplying by 10, so if 100x is around 54, then 10x would be around 5.4, and so A1 would be 5. And then you're taking your thing, which is around 54, and subtracting 50. Now you're again between 0 and 10. Okay, so let me just note, this is certainly 0 is less than this, and this is less than 10. So now you do the exact same thing of taking the largest integer away from this as you can. Okay? I'm sorry, minus 10a1 is less than 10. Okay? You take the largest element, and then what we know is that 0 is less than x minus a1 over 10 minus a2 over 100, which is less than 1 over 100. Again, to see this, just multiply everything you see by 100. You'll get 100x minus a1 minus 10a1, so you'll just get this term, minus a2, and you know that this is less than 1. Okay? So you multiply by 100 in this case to see this. I would encourage people just, pick some random decimal expansion and see that you're getting the right answer by going through this procedure. Okay? So now we continue. Okay, so continuing. This process, we get a sequence, okay, which is a1 over 10 plus a2 over 100. We would do the same thing, get a3 over 1,000, okay, plus an over 10 to the n, so that x minus this sum okay, so plus an over 10 to the n is less than 10 to the n. Oh, sorry, 1 over 10 to the n. So in other words, this sequence, so we have x minus this sequence, over 10 to the n, approaches 0, okay? And then, therefore, the sequence itself converges to x. So we get that x is a1 over 10 plus a2 over 100 plus dot dot dot. Or in other words, it's the way you write this is point a1, a2, a3, and so on. Okay, so it's easy to see, and I guess I won't do this. I'll just leave it as exercise. You can check that these decimal expansions are unique. Okay, for irrational numbers. Okay, so in other words, if I had x equaling b1, b2, b3, and so on, then every ai would have to be equal to every bi. Okay, so for rational numbers, it gets slightly trickier. Okay, so there are two possibilities. Okay, So the first is that x, or r, is just equal to one of these finite sums. Okay? This is certainly possible. Plus an over 10 to the n. So in other words, this rational number looks like, point a1, a2, up to an, and then zeros after that. Okay? So I'll say it turns out this happens exactly when r is p over q, and q looks like some power of some power of 2 times some power of 5. Okay? So this is actually, this isn't too hard to see if you just write down this expression. Okay. Since the denominator here, once you write this just as something 10 to the n times some product, okay? So you'll get an integer divided by 10 to the n. You might have some division that occurs, but since the only prime factors here are 2 and 5, you have to have the same prime factors here are 2 and 5. Okay? So you kind of know exactly when you have a terminating decimal expansion. What's slightly harder is that if r, which is p over q, is not of this form, okay, so i.e. q has prime divisors other than 2 or 5, then the decimal expansion is eventually periodic. Okay, so what this means is that r is going to be, there might be some junk at the beginning up to some point. Okay, some junk. But then after that, it's just a repeated block of the same decimal expansion. Okay, so again, there's some, B1 up through BM, B1 up through BM, B1 up through BM, and that continues indefinitely. Okay, so in particular, if Q is relatively prime to 10, then there's no junk. Okay, so in other words, what this means is that you just get a repeating term. Okay, so for example, this is why you see something like 1/3 being 0.3 repeating, or 1/7 is equal to 0.142857 repeating. This is, something that I'm not going to talk about, especially since I'm only going to continue for a couple more minutes. But this is the kind of the general story. Okay? So finally, I just wanted to end with one more thing, which is why do we say then? So why do we say that, say, 0.3999 repeating is equal to 0.4, or anytime you have a expression ending in all nines, then there's this non-uniqueness of decimal expansions. Well, this really just comes from the fact that the sum from n equals 1 to infinity of 9 over 10 to the n is equal to 1. Okay, so let me just prove this as a last thing, and this is, you can also have similarly if you want to show that the sum from n equals k to infinity of 9 over 10 to the k. Well, of course, this is just equal to 1 over 10 to the k minus 1, sum from n equals 1 to infinity of 9 over, 10 to the n. Okay, so you just get 1 over 10 to the k minus 1. And luckily, we've already done the work of this, right? So this is just 9/10 plus 9/100, and so on. From the formula for geometric series, we get that 9 over 2 to the 10 to the n is 9 times 1 over 10 to the n. This is 9/10 times sum from n equals 0 to infinity of 1 over 10 to the n. And now I can plug into my formula, so this is 9/10 times 1 over 1 minus a tenth. Okay, so in other words, this is 9/10 times 1 over 9/10, which is 1. Okay, so it follows immediately from the geometric series that you get precisely that a decimal expansion of 0.999 is going to be equal to the decimal expansion 1. And this is also, why you don't see anything else really funky going on. Okay, you can imagine that if you put in any numbers other than 9, at least, do this with something like an 8, right? Then you'll get 8/10 times 1 over 1 minus a tenth, and that's 9/10. You'll never produce 1 except for digits all being 9. Okay, so I think that's all I'm going to say. So thanks, and see you on Monday.